According to the ANSI IEEE 1059 standard, software testing is a rigorous process of analyzing a software item to detect differences between existing and required conditions. Casual usage to check for basic functionality differs from testing, which requires executing a system with the specific intent to identify gaps, errors, or missing requirements against a set of standards. Yet the software industry suffers from a deep semantic confusion. Development teams frequently conflate distinct methodologies, using terms like quality assurance and quality control interchangeably. When organizations fail to distinguish between these terms, they overlap responsibilities. This leads to inefficient engineering pipelines and poorly executed risk management, where critical defects slip through because teams assume someone else is looking for them. This graphic illustrates the software development lifecycle, or SDLC. We can use this chronological map to untangle these dichotomies and place each testing concept exactly where it belongs in the development pipeline. Building a precise mental model of this terminology is the foundation for true software quality engineering. You cannot guarantee quality if you cannot define the methods used to achieve it. The first major dichotomy separates preventive procedures from corrective execution. At the top of the quality management hierarchy sits quality assurance. It is entirely preventive and process-oriented, focusing on establishing the standards and procedures the team follows during development. QA operates with strict boundaries. It ensures that proper procedures are implemented, but never involves executing actual software to find bugs. Below QA, we find quality control. It is a corrective, product-oriented process that verifies the developed software aligns with documented requirements. Nested entirely within quality control is testing itself. Testing is the physical execution of the software with the explicit goal of identifying defects, gaps, or errors. While testers identify those defects, they do not correct them. Developers step in to debug the code, isolating the root cause and applying the fix. By explicitly separating overarching preventative process management from product-oriented corrective defect identification, engineering teams can build robust quality systems without redundant efforts. This brings us to the second major conflation, the divide between verification and validation. Verification asks, are you building it right? To answer this, developers perform static, objective checks, like code reviews and inspections, before the software is executed. Validation, on the other hand, asks, are you building the right thing? This dynamic, subjective process involves testers executing the compiled software to ensure the final product meets the intended behavioral requirements of the end user. A development team can write structurally flawless code that passes every inspection, but verifying pristine code structure is entirely useless if the final executed product fails to validate the user's actual needs. Once execution begins, testing methodologies are categorized by visibility. In black box testing, the tester has zero knowledge of the internal code. They interact with the system strictly by providing inputs and examining outputs, oblivious to internal processing. Because it ignores internal architecture, black box testing scales efficiently for massive segments of code. However, it suffers from blind coverage. The tester cannot target specific internal vulnerabilities or error-prone algorithms. White box testing, also called structural testing, is the exact opposite. Here, the tester requires complete access to and knowledge of the internal logic. This method provides maximum test coverage and is essential for optimizing complex algorithms, but it requires highly skilled software engineers and expensive maintenance tools to execute properly. Gray box testing serves as the hybrid compromise. The tester does not have full access to the source code, but they do have limited internal knowledge. By leveraging database diagrams and high-level architectural documents, a gray box tester can design highly targeted data inputs that stress-test communication pipelines without relying on redundant, trial-and-error black box methods. Black box hunts user experience flaws, white box secures code logic, and gray box stress-tests data pipelines. Choosing the correct visibility level allows a team to efficiently isolate distinct types of errors. The final dichotomy dictates the execution strategy, choosing between manual and automated testing. Manual testing remains a necessity for evaluating complex graphical interfaces performing exploratory edge case discovery, and experiencing the software as an actual end user. Automation testing is constrained by a strict threshold. It is reserved for software that is already structurally stable, scenarios that require frequent, repetitive execution, or systems that must handle massive, simultaneous data loads. To see how automation accelerates structural verification, we can observe a real-world white box unit testing setup. This screenshot displays a basic Java class featuring a mathematical sum method. A developer needs to verify its internal logic. Instead of testing inputs manually, developers utilize integrated IDE tools to rapidly generate automated testing boilerplates. During the configuration phase, the developer selects a dedicated testing framework, in this case JUnit 4, to manage the automation execution. The IDE generates the execution logic. Expected results are programmed here to assert against the system's actual mathematical output. By default, it even produces a prototype failure message if the logic isn't fully implemented. This final screenshot confirms the successful execution output, proving that the internal algorithm functions flawlessly under automated stress. Automation is a powerful optimization tool for verifying internal structural integrity, but scripts cannot interpret user frustration. It cannot replace the manual tester's ability to validate the human experience. Looking back at the complete software development lifecycle diagram, we can map out exactly where these defined concepts belong. Quality assurance and static verification sit securely in the early planning and defining phases. Establishing processes here prevents expensive code rework later. Developer-driven debugging and structural white box testing map strictly onto the software's building phase, securing the foundation as it is written. Validation, quality control, and black box testing occupy the testing phase, ensuring the product matches user expectations. Finally, automated testing scripts function as a continuous, repeating loop deployed throughout the final deployment and maintenance phases to catch regressions. Testing is a continuous process that acknowledges a technical limitation. No software system, regardless of complexity, can be tested to 100% perfection. Mastering these dichotomies means deploying the right methodology at the exact right time in the development cycle. That is how engineering teams efficiently manage risk, isolate defects, and guarantee real-world software stability.